This is video 531 to go along with section 5.3 in your textbook. We're going to look at a few more formulas that help us find exact values and verify trig identities. So this video will look at mostly finding exact values. So first of all, the double angle formulas are pretty straightforward. What's nice is for cosine you have multiple formulas that you could use depending on what you want to introduce. This will come especially handy when we're looking for ways to get rid of sines and cosines, or to only introduce sines or cosines when verifying identities. Let's take a look at this first problem. I always start with drawing a picture of the proper angle. It has to be between pi over 2 and pi. So my angle's over here. It has a y value of 3 and a radius of 5. So I know this has to be negative, and it's negative 4 by Pythagorean triples. So why is this important to draw a picture? Because I need sine of 2 theta, which requires me to have the sine of theta and the cosine of theta. I had the sine of theta to begin with, but I need the cosine of theta, and from my picture I can see that it's negative 4/5. So now I'll simply plug into my formula to find the sine of 2 theta for this particular theta. I'm going to do 2 times the sine of theta, cosine of theta. Replacing those with the proper values, the sine of theta is 3/5. Cosine of theta is negative 4/5. Multiply these fractions out, and I get negative 24 over 25. Here is my exact answer for this cosine, the sine of 2 theta, where theta is between pi over 2 and pi, and sine of theta is 3/5. Now let's take a look at how to use the half angle formula. So this is the opposite. Once again, we're given an angle, and now we want information about half of that angle. So we're trying to find the value of cosine of theta over 2. So we start with drawing a picture again so we can visualize our angle. It's going to be in the third quadrant, and it's going to have a tangent of 1/2. So the rise is 1 and the run is 2, but they're both negative because they're in quadrant 3. In order to find the cosine of theta over 2, I need the cosine of theta. So if I need the cosine of theta, I need the cosine of this angle right here, but I need the hypotenuse, the radius, in order to do that. So I'm going to solve for that by using the Pythagorean theorem. Work it out. Get 1 plus 4 equals r squared. 5 is r squared, or square root of 5 equals r. I know it has to be positive square root of 5 because the radius is never negative. Only the x and y values will be negative. So now my cosine of theta is negative 2 over square root of 5. And that's an important value that I need in order to plug into my formula here. So now, the next thing that we need to understand about the formula, we now have what we need to plug in, but we see these two options. Those two options are dependent on, we need to know what the value of the cosine of alpha over 2, will the cosine be positive or negative at that angle? So in looking at our picture, we have an angle, if it helps you to change it to degrees, we have an angle between 90 and 270. I'm sorry, 180 and 270. We have an angle between 180 and 270. So an angle half that size, because that's my goal, the cosine of theta over 2. An angle half that size would be between 90 and 135. So I know that angle is going to fall somewhere in here. This is 90 degrees, and this is 135. So my angle is going to fall somewhere in here. Now I ask myself, is the cosine positive in that section of the unit circle or of any circle? And it is a negative cosine there because the x value is negative. So now I know I should be using the negative form of the equation, not the positive. Everything else would stay the same, but that negative or plus or minus depends on what the cosine will be at that point on the unit circle. So now we're going to plug into my formula accordingly. Plug in cosine of theta, keep my negative on the square root. So we have negative square root 1 plus 2 over square root of 5, all over 2. So I have this fraction within fraction, I have a radical and a denominator. All these things need to be fixed before I can give a proper answer. So in order to make this proper, I'm going to start with getting a single fraction up top by making this a common denominator of 2. So I'm changing my 1 to 2 over 2. So my numerator becomes, I'm sorry, square root of 5 over square root of 5, not 2 over 2. My numerator comes square root of 5 over square root of 5, because that was my denominator here. So I'm going to have square root of 5 plus 2 in the numerator of the top fraction, all over square root of 5. That's what the numerator turns into. Now, I also want to figure out how to take care of that 2, so I'm going to change it to multiplying by 1/2. Dividing by 2 is the same as multiplying by 1/2. So get used to doing that flipping to allow you to have multiplication instead of division. So in this big radical now that has a negative in front, I have a much simpler problem. So let's take a look. On the top, multiplying by the 1 is easy. On the bottom, multiplying by the 2 is easy. So we're left with the negative square root of square root of 5 plus 2 all over 2 square roots of 5. So now I need to figure out a way to make my denominator proper. So right now, if I were to split this into 2 radicals, top and bottom, which is a proper way to work with radicals, I would have a radical in the bottom that I can't simplify. So this is not going to help me yet. So I'm going to work with this fraction, and I'm going to slowly turn it into a proper fraction. It's going to take a little bit of work. So first of all, I know if I multiply the top and bottom by 2 square roots of 5, I would at least get a nice whole number in the denominator. Okay, so I'm going to start by doing that. So 2 square roots of 5 times 2 square roots of 5 is going to be 4 times 5 all over, let's see, I'm going to distribute on the top. I'm going to have 2 times 5 plus 4 square roots of 5. So remember, you can multiply in any order, so that's why I'm turning these 2 5s, these 2 square roots of 5, into a single 5, because the square root of 5 times square root of 5 is just 5, and then the 2 follows. So this is a slightly simpler. I have a nice whole number in the bottom now. I have a nice 20 in the bottom, so I'm going to replace that 4 times 5 with 20. And I'm going to replace the 2 times 5 with 10. And I have plus 4 square roots of 5. So now the bottom, I still can't take the square root of 20. So I think, okay, how can I turn that into something I can take the square root of? And I think of 100. If I times the top and bottom by 5, I get a perfect square in the denominator, which I can take the square root of. So now in the numerator, I have distribute the 5. We're working inside of the radical. That 5 times 5 is inside the radical. So I'm going to have 50 plus 20 square roots of 5 all over. In the bottom, I'll have the square root of 100, which is exactly what I was looking for, a perfect square. So my result, my final, proper answer, I need to have a negative in front. My proper answer is negative square root of 50 plus 20 square roots of 5 all over 10. That's a proper answer. It is as simple as you can get. So that's a working through with the radicals. We're working on all those skills so that we can be stronger for calculus. Let's take a look at another example. So here we have 2 more examples. We're trying to find the exact value, and they are half-angle formulas. So 15 degrees is not your alpha for your formula. It's actually your alpha over 2. So we can rewrite 15 degrees as 30 divided by 2. So in this case, our alpha that we're going to work with here is 30 degrees. So we're going to find the cosine of 30 over 2 by doing the square root of, we think of whether it's going to be positive or negative. So 15 degrees, will the cosine be positive or negative at 15 degrees? Well, there's 15, and the cosine will be positive there, because cosine and sine are both positive. So it's going to be positive square root of 1 plus the cosine of 30 all over 2. Okay, because I knew 30 divided by 2 is 15, so I can use my half-angle formula for this situation. So let's see, we got to simplify this and replace the cosine of 30 with what it's equal to. The cosine of 30 is square root of 3 over 3. over 2, excuse me. Square root of 3 over 2. And then this is all over 2 still. So that radical should go all the way down. So now once again I want to make this proper and simplify it so I get a common denominator of 2. And I'm going to change this to 2 plus the square root of 3 all over 2. That's just the numerator. But in changing the denominator, instead of dividing by 2, I'm going to change that dividing by 2 to timesing by 1/2. Same exact result. This will give me a lot simpler answer of 2 plus the square root of 3 all over 4. This one's going to work out in my favor because the denominator is a perfect square. So if I separate the numerator from the denominator, I will get the square root of 4 in the denominator, and that is a simple 2. So my exact answer for the square root of 15 is square root of 2 plus square root of 3 all over 2. This is your final answer for the exact value of the cosine of 15 degrees. So remember, if you need to go back, pause, rewind, whatnot, I'm going to jump to the next example so we can get this video done in 15 minutes. So let's see here. So tangent of 3 pi over 8. There is a way to use the half angle formula. So I'm going to factor out that divide by 2 and rewrite 3 pi over 8 as 3 pi over 4 divided by 2. This is equivalent to 3 pi over 8. Okay, so 3 pi over 4 is my alpha in this case. So I'm going to be working with one of these formulas. It won't really matter which one I choose in this case because I'm not necessarily verifying an identity. So I'm just going to work with cosine. I'm going to work with the first one, all over sine of 3 pi over 4. And I'm going to replace what I know about cosine of 3 pi over 4 and sine of 3 pi over 4. Cosine of 3 pi over 4 is negative square root of 2 over 2. So it looks like I'm going to be having 1 minus a negative square root of 2 over 2. And then the sine of 3 pi over 4 is positive square root of 2 over 2. So this is all over the square root of 2 over 2. So once again, fractions within fractions, but at least there's no mega radical here. I'm going to change this to adding a positive, and I'm also going to change to have a common denominator of 2. So it looks like I have 2 plus the square root of 2 all over 2 for my numerator. I'm going to once again change this to multiplying by the reciprocal, 2 over square root of 2. So that makes my life a little simpler here. I'm going to distribute this 2 out, and I'm going to rewrite the bottom. So I have 2 times 2, which is 4, plus 2 square roots of 2, all over 2 square roots of 2. So this is great. It's almost simplified. I have a radical in the bottom. To get rid of that, I'm going to times top and bottom by square root of 2. This will allow me to cancel out the square roots of 2. So whenever you're trying to get rid of a radical, you're going to multiply top and bottom by that radical. So the denominator becomes, this square root of 2 just becomes a 2, and then times the 2 that was originally there. So on the bottom, I'm going to have 4. And on the top, I'm going to distribute this 2 in order to make it proper. And I'm going to have 4 square roots of 2 plus, once again, I'm going to have the same thing here. I'm going to have 4 just like I had in the denominator. It looks like this simplifies even more if I separate the fractions. So it looks like 4 square root of 2 over 4 for the first fraction plus 4 over 4. Well, once again, this is a nice simple fraction. I can make this really simple by just changing it to, this will cancel here and make just square root of 2 plus 1 from here. That is the simplified answer for the tangent of 3 pi over 8. Here are your first 3 checkpoint exercises to try. Use the examples as a guide. Remember, there's more information in your textbook for section 5.3, more examples to help you through this. But bring in your questions to class when this assignment is due.